Alright, I'm chilly. Let's get on with it. Making a motherfucking game. After I burp. I'm all caffeinated. I'm ready to go. So, today we're going to work on the shield. We're going to make it so that the shield can take damage and shit. But, first of all, let's just, let me just recap here. We'll take a zoom out, take a little gander at the bigger picture. So, right now we're working on very basic features. The bare minimum features for the engine. We're going to want shield damage. That's what we're working on right now. Then we're going to want to be able to track a ship around the course in order to determine whether it has completed a lap. And finally, I want to add the mechanics for the black hole, a little bit of physics in there. Once we have that, we have basically what you might refer to as an alpha. And then we can start working on something to package it all together and make it more like a game, adding a menu, adding a way to track progress, maybe adding some controller support and shit. And once we get that all together, then we can work on the bells and the whistles and tweaking the gameplay. But that's all for the future today, working on the shield. So, let's have at her. So we got our, I hope this is HUGS. I think it is. Let's go to unsynced commits. We'll click on sync. Make sure we've got all our shit up to date. Then what we're going to want to do is go to branches, new branch, and shield. That's the new one. Create that branch. Click on it. Go to solution. And there we go. We've got the solution all opened already. But we don't want to do that. We want to look at what changed. So we're going to go to changes and we're going to do what? Actions, view history. There we go. Okay. So here's where we left off. The inside, outside. So the first thing that I ended up doing for this this video portion here is I went ahead and I created a object to display the shield status on the screen, a meter object. So the first thing we needed for that is we need to be able to draw rectangles, because we don't really have a good function to do that. So what I did was I went into, let's see, D3D graphics. I added a draw rectangle function here, templated, mind you. And I also added templating to the draw line function just because I wanted to. And I think I changed these triangle functions. I made the reference to the rectangle constant, which is not a big deal. Just, I don't know, just my OCD. Then in here, we do the draw a rectangle. Very simple. I don't think this needs any explanation. Just a simple loop. I debated internally for a while whether I should make it inclusive or exclusive. That meaning the end extent, whether that pixel would be lit up or whether it would be not lit up. And I decided we're going to light them all up. So for example, if you're going to draw from... if the left boundary was at 0 and the right boundary was at 1, then you're going to light up the 0 column and the 1 column. What else did I do? Oh, I just put in game.cpp. I put a simple line in here to test my draw rectangle. And in vec2, that's weird. What did I do here? Oh, yeah. Okay, so I added a type definition for integer vectors, because that's what we needed for draw a rectangle here. It's funny, I didn't add an override for an actual rectangle. It was a little bit of an oversight, but whatever. If I ever need it, I'll add that in there. So that's that. Draw a rectangle, very simple. It draws a rectangle on the screen. Now here is something I just want to talk about quickly. I started writing the shield meter class. What I did is I wrote a function for ship to get the percentage of shield remaining, where 1 is equal to full shields and 0 is completely depleted. Then I created a new file called shield meter, and this is a drawable object. Well, you can get a drawable from it and draw it, and yeah, it just draws the it's responsible for drawing the meter on the screen. So it maintains a reference to the ship, and it uses that reference to get the shield percent and then draw that on the screen as a graphical meter. But I started writing it, and then I had to create the video for episode 3, I guess it was. And to do that, I had to switch branches. But here's the thing about Git and stuff like that. If you haven't committed any code, you can't just switch your branches. You can't check out a different branch. Because if you check that branch out, all the code that you've written will be lost unless you commit it. But if you're only halfway through and you're working on your shit and you write a commit for that, it looks kind of dumb because it's like a half-assed chunk of code that you're committing and doesn't make any sense. It's not a cohesive unit. So it's not very good, and I'm going to teach you a way of switching branches without making these half-assed commits. I will teach you 2 ways of doing this because, hell, that's how awesome I am. Actually, shit. One of the ways I want to teach you, I forgot how to do it. Let me take a second here. Wait, I know what it is. It's git stash. But I don't know the exact, what do you call it? The exact syntax. So wait a second. All right, so apparently the command is git stash and git stash pop. Now these are git command line commands. So where's my fucking git shit? There it is. They're actually not in the git GUI. So let me go here. Let me just check some shit out here. Yeah, if we go to tools, add, remove. Okay, so visualize all branch history. So we can't git stash from git GUI because it doesn't have that command, but we can add that command to our git GUI. So let me just give you a demonstration of how this is going to work. I'm going to open up file here, and I'm just going to make some modification to the source file. Dumb. And if we go to this, go to branches, and let's say we try to switch to master branch. It says you want to save changes. Okay, sure. Then it says cannot switch to master because there are uncommitted changes. Commit or undo your changes. So you can, you can go to changes, click on this and go undo if you just want to, if you don't care about the changes that you made. But let's say we've made some, really important changes to the source file here and we just can't lose that work. What options do we have? Well, one option is to do git stash. You can do it from the command line if you know how to do that, but let's say you don't. We'll just add a new command. We'll call it stash. And the command is stash. I don't think you have to type git. Whatever. Add. Now let's click on stash. Stash command not found. Shit. Let's try. Let's try stash, git stash. Let's try adding that. Tools, stash. It worked. Okay, so now we have stashed our changes. Yes. Now if we try to change our branch, we can switch branches, no problem. And let's go branch. Let's go back to shield branch. Cannot switch to shield because there are uncommitted changes. What the fuck? These files doesn't like the way. Let's just undo that. We'll just undo that. It's kind of annoying, but something that must have been left over from the previous branch that we switched from, and then it recognized it as a change. I don't really know. Now we'll switch back to shield. Now if we look back to where our shit was here, you notice that our line that we added does not exist here. But we can retrieve that change by going into the Git GUI. Tools will add. We'll call this one git stash. And the command is git stash pop. And that should retrieve our stashed changes. So we'll call get stash. Change this one, reload, and there's our shit. And then we can continue working on our change, and when it's complete, then we can commit the change. But since it's not anything that we actually want to do, I'm just gonna fucking not commit it. Now there's another thing we can do. So let's say I want to change, can't change. No, you can't switch. Okay. What you can do is you can create a temporary commit by going changes, commit, and we'll go temp commit to change branch. You commit that shit. And now that commit is done, so we can now switch branches. Then we switch back, and we've got our stuff here. And like I said, you don't want this dumb commit in the middle of your branch here, just fucking shit up. Let me just go update. We don't want this shit here, it kind of sucks. But then when you're finished and you actually want to make your real commit, what you can do is you can add those changes to the previous commit and also change the name of that commit. So it actually looks like that commit never happened. So you go to changes, and you're going to type in here, changes all done. And you go actions, amend previous commit. And that will fix the old commit and add the new stuff into it to make a single complete commit instead of having two separate half-assed commits. So then if we go HUGS and we go reload, now we see changes all done. We don't see that temporary commit that we added there. Now, here's one thing I want to try. I want to see if I can delete this commit from... I don't want to revert the commit. I want to kill it completely. I don't know how to do that, though. That's the problem. So I'm not going to try. But there's definitely should be a way to do it. I just don't know how. So I'm just going to leave this commit on here. It's going to be kind of dumb, but it doesn't matter. Not important. Okay, so that was a little bit of a Git tutorial there on how to temporarily stash your commits or your changes so that you can change branches. Now back to our regularly scheduled programming. So, let's see here. This test meter thing here is where I finished the code for the meter. Wait, I didn't actually talk about it too much. Let me go back here. Just talk a little bit about it. So the shield meter thing, it has a drawable object inside of it. And the rasterize function is going to do all the drawing of the meter. The shield meter itself, like I said, maintains a reference to the ship to get the information about the shield. And it maintains a rectangle to get the information about the region, which is the size and location of the meter. Then it has the color of the border. It has the width of the border and the spacing between the border and the actual meter itself. So the meter is going to look something like this. Let's get a new layer in here. It's going to look something like this. You've got a meter, or you've got a border, and then inside you've got a meter. And this meter's representation depends on the value of the shield. So when the shield is low, it's going to look like this. Very simple, very straightforward. Let's continue. Go to history. So test meter is where I finished writing the meter. And it's just a bunch of draw rectangles to draw the border. This is drawing the top. This is drawing the left side, right side, the bottom of the border. And this is drawing the actual meter itself, I think. Let's see here. Yeah, meter color. So this is drawing the actual meter itself. So 5 rectangles make up the meter. I make the color of the meter also change depending on the value of the shield. Now this fucking branch actually doesn't work because for some reason I committed this, but I didn't fix all the bugs. So I don't know why I committed this. But anyways, this one, although it just says switch branches, it actually fixes the bugs. And it also changes. So originally, just to for testing purposes, I set get shield percent just to always return 1. But since that doesn't let us test the meter for various values, I changed it so that it returns velocity divided by maximum speed, which gives us basically a value from 0 to 1 representing how much percent of our maximum speed we're traveling at. And then I fixed some problems here and here, small bugs with the rectangles and the color. And this is the bug that caused the thing to crash. And I just had the left and right and the top and bottom values messed up for the rectangle. The rectangle you use to create the meter defines the outside of the frame of the meter. So if you make a small rectangle, you're going to get a small meter. You make a big rectangle, you're going to get a big meter. And where you make the rectangle will determine where the meter appears on the screen. All right. So, I didn't want to close everything. There we go. So this actually has everything working. And I'm just going to create a quick branch to demonstrate. I don't want this one. Let's just fucking close this off. I'm gonna close you down, motherfucker. So this was switch branches. I'm gonna create new branch. Test. And I'm gonna check it out. Reload. Start without debugging. So here's what this motherfucker looks like. Well, let me get a little bit more into the screen here. So as you can see, as we speed up, the meter goes. And it gets red as it fills up, which is backwards from what I want, because what I want is full shield should be white. And as the meter depletes, it gets more and more red, signaling danger, right? Danger, Will Robinson, danger. But that's not the way it worked because I fucked it up. But anyways, close enough. Let's continue. So collision damage, here is where I actually have collision with the wall reduce the value of the shield. So what I do is I add a couple new members to the ship. Let me get someone to drink. Add a couple of new members, the level of the shield, and also the max damage that you can get from one collision. So conceptually, max damage equals the amount of damage that you receive when you collide head-on with a obstacle at maximum speed. And that's reflected in this line here. Let's see if I can find anything else. All right, so I switched this back from speed back to actual shield level because now we have damage, so our shield level will actually change. And here, so when we actually bounce off an obstacle, we get this rebound message with the normal. And since we already know our own speed and we know the normal that we're bouncing off of, we have all the information we need to calculate the damage right in this rebound. So we don't need to add anything new to, for example, polyclosed here in the handle collision or something. We don't need to change any of that shit. All our work is done in this rebound. And all we're doing is we take the shield level and we subtract from it the amount of damage. The amount of damage is equal to our maximum damage multiplied by the dot product of our velocity and the normal of the wall that we're colliding with. Right? So with the dot product being very high, meaning we're hitting the wall right on. If the dot product is very small, we're just doing a glancing blow and we shouldn't take that much damage at all. And we're just scaling that by maximum speed. And that's what we get. We have to put a negative in here. We have to negate either the normal or the velocity so that the vectors are pointing in the same direction. Because normally the velocity and the normal are opposed. So if you take the dot product, you get a negative value. So we need to negate that to get a positive value. Very simple. And then we just take the maximum of this result and 0 to make sure that if the damage reduces the shield level below 0, the shield level will just be equal to 0. We don't want negative values for the shield level. And that is all she wrote. So if let me just check something out here. Let's check the history. All right. Then what I did was change the color and length of meter. So I changed the color so that the shield turns red, the meter turns red as the shield gets weaker. And I changed the length of the meter. I made an adjustment here because remember when I said, talking about the draw a rectangle and how it's inclusive? The way that works is with the old code here on the left-hand side, with, let me just do that. With this code, a shield value of 0 would still show a little sliver of meter. And we want no meter if the shield value is 0. So we had to actually adjust by -1 here to take into account the fact that the drawing of the rectangle is inclusive. And if we create another test here, create a new branch, test 2, check this one out. Hope it doesn't crash. And move the thing here into the recording window. So now we're going to now we see the shield being reduced and getting red as we bounce off the walls. And then staying at 0 once it reaches 0. Very good. So I figured this was a little too short for one video, so I decided to add some more stuff onto my plate. Next thing we do is we figure out a way of communicating when when the shield reaches 0 and we have a collision. So basically, colliding at a shield value of 0 will equal like the death of the ship, which is going to be like a game over, right? So we want a way of figuring that out at the top level, the level of the game. We want to know when the ship blows up. So we're not going to be worrying about graphics for the ship dying or anything. We just want to know when it happens. So the way we do this, the way I chose to do this is to add an observer class here. We're going to use the observer pattern, which bears a little bit of talking about. It's probably the simplest design pattern for object-oriented programming. The most commonly used one, probably the one that they first teach you in university. And the idea is very simple. You have an observable class and you have an observer. Now, observer is abstract. Observable is not abstract, but it doesn't really have much interesting in it. Now, observer is going to maintain references to multiple observers, one or more observers. And what happens is when some event happens, it is going to notify all these observers and it is going to call a virtual void on notify or something like that, event or something like that. Something happens, it's going to call this virtual function. And what you're going to have is you're going to have some kind of class that inherits from this one. We're going to call this one Mick class. Because I've been eating a lot of McDonald's flurries lately. I love those fucking things, man. They're so good. And it's going to override on notify, and it's going to have some behavior. It's going to take some action when it receives a notification of some event. And then you're generally going to have a class that inherits from observable, and it's going to do some shit, and some of the shit is going to involve calling the on notify, it's going to call on notify for every one of the observers. And that's the way it works. The reason you do this is to decouple the observer from the observable, because they don't have to know about what kind of thing is listening, what kind of class is issuing the events. And that's very good for us, because in our situation, the thing that's going to be issuing the command is the ship. It's going to be issuing the notification. And the thing that's going to be receiving the notification is the game. Now, game knows about ship, but ship doesn't know about game. And if we make ship know about game, game is going to include ship, ship is going to include game. You're going to have a circular reference there, a circular dependency. And then you're going to have to use, what is it called? What's the name of the thing? Forward declaration, that's what it is. You're going to have to use forward declaration, and ship, the way we have it right now is in one header file. So if we had to use forward declaration, then we'd have to add a CPP file. So much work. Who cares about that shit? Ain't nobody got time for that. What we're going to do is we're going to decouple the game from the ship from the game in terms of ship giving notifications to game. And we're just going to use the observable pattern. Blah, 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 blah. Okay, so how does it work in code? Ignore these three because I didn't actually implement them properly. I'll fix it later. The way that this motherfucking bullshit works is the observable maintains a vector of pointers to observers. And all observers are classes which inherit from observer, and that means that they guarantee that they have an onNotify method, a handler for notifications. And you have your add observer function and your remove observer. Add observer adds observers to the vector, remove removes them. And then you have a protected function called notify. And what notify does is it calls notify for every observer. So it's protected so that the class that inherits from observable is able to access notify and call it. So the ship is going to inherit from observable, and it is going to call notify when it explodes. Now I added this disable, enable, and so forth in here so that you could disable the issuing of notifications, but I forgot to put a check in here. What I should have in here is, I can't edit this file, but I should have if not, or if enabled, then for all observers notify, right? But I forgot to put that in there, so fuck me. So this doesn't mean anything at the moment, but it can be useful sometimes, and I'll probably fix it later. Okay. So we have our observer and our observable. For ship, we inherit from both collidable circle and observable. Now, people say that multiple inheritance is very bad, and they're mostly true, they're mostly right, except when you're inheriting from classes which consist solely of which don't have any data. It's not so bad. It's when you get classes with data that things start to really get messed up. Inheriting from multiple virtual classes is the same idea as having interfaces in Java. And you can have multiple interfaces, that's no problem. So, we inherit from collidable circle and observable, because the ship is both a collidable circle and it is observable. We include observer. And down here in rebound, we add an additional check to see if the shield level is above 0. If it's above 0, we do the normal processing, reducing the shield level by the damage. But if it is 0 or less, although it should never be less, then we have rebounded with 0 shield, and that indicates that we should explode, and we got to notify that we have exploded. In game, I inherit from observer so that game can observe the ship. Now, later on, I'm not going to have game inherit from observer. I'm going to have an object inside of game inherit from observer, and that object is going to handle the explosion. But for now, we'll just have game directly inherit from observer. We'll add the virtual function, the override. And in game here, in the override function, all we're going to do is close the program when we die. Because that's all I can really do at this point. Just a little note in here. I don't like to mix platform-dependent code and independent code together. For later on, if you want to port a game, it's very bad if you have a bunch of, for example, Windows functions calls inside of your game logic code. You want to keep that shit as separate as possible. But for now, I didn't want to create a platform decoupling layer to decouple the Windows stuff from the general idea of closing the program. So I just put the direct call right in here. But I just wanted to add a little note that that's not what we want to do in general. All right. So if I create another branch here, create a new branch, test 3. Check that branch out. Yeah, whatever. Run that motherfucker. Now, bite me, motherfucker. Yeah, you saw a little weird thing that happens there when you drag the window. We got to fix that sometime. Oh, there we go. So what happens is the program closes when we take damage, right? Damage, losing shields, and bam, program over. So that's exactly what we wanted to happen. Everything is working according to plan and design. So at this point I was like, I could still do a little bit more in this tutorial. So I added the next thing. I want to be able to have, instead of just having the program abruptly close, I want to be able to display, game over. So I want the game to stop processing and just display a game over screen. In order to do that, I'm going to need a game over screen. I could create it as a bitmap and render that to the screen. But I would like instead to be able to just draw the text. Now, we don't have any text drawing routines in this framework as of right now. So we're going to add that, or I should say that I have added that. And I've decided to use GDI Plus to do the text for this engine, because it's a lot of work to create a font bitmap and, then load it. Well, I mean, loading the font and rendering it isn't too bad, but creating it is a pain in the ass. And then it limits us only to fixed width fonts, unless we want to get super fancy with our font rendering and layout, which we don't want to do. So instead of limiting ourselves and giving ourselves the extra work of creating a font bitmap, we are going to use GDI Plus, and that'll handle all the layout and font stuff for us. Rasterization. So I add the stuff to work with GDI Plus for fonts into the surface class, because that's where the buffer is going to be that we're acting on. Now, GDI Plus requires something called a graphics object in order to render. It's basically a HDC, or handle to device context, that is in normal GDI. So if you've ever written just a standard Windows program with Paint, with GDI painting, then you'll know what that is. But it needs a graphics object, needs a device context in order to do its rendering. Now, all our rendering is just to a simple buffer in memory, right? A simple block of memory, of pixels. And that's the problem. We can't get a graphics context for that. Things you can get graphics context for are, for example, screens, or windows, and maybe the printer. You can get a device context for that, probably. And you can get device context for a bitmap, like an image file that you open up in GDI Plus and you draw to. But what we can do is there are many different ways of, many different constructors for the bitmap object. And one of the constructors allows you to create a bitmap where you already allocate the buffer for it in memory. So you allocate the buffer for the pixel data in memory, and then you create a bitmap object that uses that buffer as its image data. And that's what we're going to do. We're going to create a bitmap, and that bitmap is going to be linked to the surface buffer that we're using to draw all our graphics. And then we can use that bitmap as a way for GDI to draw to our surface, our back buffer, or our system buffer, if you will. So what we do is we add the bitmap, and we add this graphics object here. And we create the bitmap by using the width and the height of the surface. The pitch is just the width and the height. I guess this is the pitch in bytes. So it's just pitch of our surface in pixels times the size of the color object, or color class object, I guess, which is just a pixel, right? Then you have to tell it the pixel format that you're going to be using for this bitmap. R1 is 32 bits alpha RGB. And then we give it a pointer to the actual buffer. And that's just this one here. And that creates the bitmap pointing to that buffer with the correct size and the correct format. And then we create a graphics object based on that bitmap, and we just pass it a pointer to the bitmap. And we do that in this constructor. We do it in this constructor here. This is just a move constructor to move one surface to another. I don't think I use it, but it might come in handy someday. And down here we have a private constructor for reasons I forget, but it's the same deal. So here we go. We create our shit. And then when we want to draw a string, we just use our GDI calls. So we pass a string in there, vec2 for the point where we want to draw the string. Font is a class I created. We'll talk about that in a second. And color is the color of the text we want to draw. We create a GDI plus color object based on the color we pass in. We create a brush based on that color. And then we call draw string in the GDI. API. Too many I's. It's a member of the graphics object. So we call draw string with all this important shit. I don't know what -1 does, but I'm sure it's important for something. And we pass it the font, and we pass it the point. We got to convert that to a GDI plus point because this is still in our own vector format. And we pass it the brush, and it draws the string at the spot with the font that we want in the color and the size and all the good stuff. Yeah, I'm out of water. Okay. So that's one drawstring, a very simple one. Now, there's another drawstring because there are many overloads of drawstring in GDI plus. So this one is a little more sophisticated. Now, instead of passing a point in, we pass a rectangle. And it draws the text inside that rectangle. So it does word wrapping and font layout, text layout, all for us. A bunch of calculations, all done. We don't have to think about anything. So good. The rest is the same. You pass it the font, you pass it the color. But we also pass it an alignment. So you can align the text to the left or the right or the center based on this value. And that's based on the rectangle you pass. So it'll align the text in the center of the rectangle or to the left or the right of the rectangle. And this is very useful for if you want to have like text boxes, you have an RPG or something, you've got like extended text. It'll lay it all out for you in a box. Good for user interface and stuff like that. Just good. It's just so good. So first thing we do is we switch the kind of alignment that we want, and then we set this, there's a string format object that we create before the switch, and we set it depending on what kind of alignment we want. So if it's left alignment, string alignment near, right is far, and center is center. Then just like before, we create the text color, we create the brush based on the color. We draw the string with all the information. I'm kind of interested in what this -1 is for, but you can look it up if you want. You just got to look up GDI plus drawstring. It's on MSDN. It'll give you a list of all the parameters and what they do. And that's how we do drawstring. Now, two little caveats. First of all, since we're using GDI plus functions, we need to initialize the GDI plus engine. There's a function to initialize the GDI plus, and there's another function to shut it down when you're done. And if you do not call that function, you just start trying to create a bitmap, or you try to create this graphics, or you try to draw a string, your program's just going to puke because everything's not set up. So you need to set that shit up. Now the problem is is if we were to call that setup function in the constructor, it would be too late because we're already using GDI plus before we enter the body of the constructor, because we use GDI plus in the initializer list here to initialize this bullshit. So we'd have to initialize GDI plus outside of the surface. We'd have to do it in D3D graphics or something. But I have a sneaky way of initializing something before you initialize something for an object inside that object's constructor, but before another thing in the initializer list. So before the body of the constructor. And the way to do that is to create an initializer object or a class. So I call this class the GDI plus manager. And it has a constructor and a destructor. And it also carries a token here. And what it does is its constructor just calls that startup function, GDI plus startup, here, and it remembers the token. And in here, it calls GDI plus shutdown with the token. And in doing so, we put the GDI plus startup object. Wait, no, here it is, D3D graphics. Okay, so I put the GDI plus manager in D3D graphics, and just by including this one object, doing nothing else, that'll create, when it gets constructed, that will initialize GDI, and when it gets destroyed, that will shut down GDI. Very simple. And I like this idea of having a class that doesn't really do anything. It's just its only work is done when it's constructed and when it's destroyed. I use this pattern for seeding the random numbers. I'll do that later. But so yeah, that's all the GDI plus manager does. It manages the startup and then shutdown. Now I fucked up here in that I also have GDI startup and shutdown in another part. When we create a surface from a file, meaning we load an image, I also call GDI startup and shutdown. And also when we're saving, I don't know if I have it in here somewhere. Yeah, here we go. Save. So when we save a surface to file, I also call GDI plus startup and shutdown. But I shouldn't have to do this anymore because it should be done in graphics. So since it's done here, I shouldn't be calling it anywhere else. So I'll have to remove that later. But anyways, font is a very simple function. It's just a wrapper for GDI plus font. So it holds a font object. And when you construct the font here, it constructs that GDI plus font. And it also, this is where the alignment enumeration is declared. And it has an operator here that just allows you to pass this directly to GDI plus functions, because GDI plus functions, they require pointers to their objects. This just converts it to a pointer. So yeah, that's all that shit is. So it's fairly straightforward to draw text with the GDI plus. The only tricky thing is creating that bitmap around our pixel data from the surface. So creating the bitmap in place in memory and then using that as a window for GDI plus to work its magic on our surface. That's just a little bit of trickiness there, but nothing too hacky. A little note here, I forgot to mention something. So I told you that we added drawString functions to our surface so that we could render text to the surface via GDI plus. But what I failed to mention is that we also had to add those functions to graphics, because surface is a private member of our graphics, and we needed to expose that functionality to the outside world, so that our our objects in our game can use these functions to rasterize text to the surface. So we create these functions, inline functions here in D3D graphics, and all that does is it passes the information through into the drawString function of our surface, our sysbuffer surface. That is all. And then I implement a game over screen. Basically, I add a font and I add a Boolean value, sentinel value for remembering whether the game is over or not. And initialize the font to Times New Roman 60 point. And down here, game over. So now on notify, instead of just quitting the game, we set game over is equal to true. Then in the update, if the game is not over, we do the update. And in the compose, if the game is not over, we draw the ship and we focus the camera on the ship and draw it. Then we draw the map in either case, whether the game is over or not. And then if the game is over, we draw the game over string. And finally, thank God, because my throat is so goddamn dry. Finally, I just tweak some values for the damage of the ship and the speed, make it a little more challenging. So, this is the end of the branch. So if I go to branches and I switch from test to shield, start without debugging. So now you see the end result. So if I can make it, see if I can make it around the track without dying here. Whoa, shit. Whoa, fuck. Okay, there we go. All right. Oh, fuck. No. Shit. Oh, no, don't do that. Okay, I'm so close. Motherfucker. Ah, I was so close. But anyways, so that's the way it is. And once you reach the game over state, you can't do anything except close the game. So, that's how it is. That's how it be. People don't think it be like it is, but it do. Anyways, so next lesson. Where's my shit? Where's my motherfucking shit? Yeah, look up. I recommend you look up the observer pattern. It's very interesting. It's one of the most famous gang of 4 patterns, and we'll be using it a little bit more. Not for everything, but we'll be using it more in the future for this game engine. And I can't remember if we used it before in anything else, but we might have. So the next video is going to be on tracking a ship around the track, making sure that it doesn't do anything stupid to complete a lap. Like, for example, let's say you have a track. Where's my motherfucking layer? That's not what I wanted. There we go. So let's say you've got a track. This part of the track is right here. And this is the finish line. You don't want the player to just be able to go like this, then come around back, and then go like this, and that's one lap, right? You obviously want to be able to track them around the track, make sure they take a complete path around the track in order to make one lap. So I will be presenting the solution to that problem in the next tutorial. But for now, I will bid you adieu and happy coding.